For thousands of years, human engineering has been defined by a constant wrestling match with gravity. To build tall, you need stable ground, anchoring deep into the earth to support the massive downward weight. The Burj Dubai in the United Arab Emirates represents the final limits of this earthbound logic. It climbs nearly a full kilometer into the sky, standing 818 meters tall. Reaching that height requires a staggering amount of mass. This technical page from our source text points out that the reinforced concrete in the Burj Dubai weighs the same as about 100,000 elephants. This weight is necessary to keep the tower from toppling. But a design based on heavy mass fails the moment you leave solid ground. Architects have to solve an entirely different set of problems when building in places where the landscape moves, where pressure is crushing, or gravity doesn't exist. To survive beyond predictable terrain, designers had to rethink the concept of the building entirely, moving away from heavy, static concrete blocks. The shift toward adaptability began with the development of lightweight materials. Specialized plastics and high-tech glass gave engineers the ability to construct shapes that are far lighter than traditional masonry or concrete. The O2 Arena in London uses a flexible dome supported by 12 support towers, one for every month of the year. This roof material allows the structure to span 365 meters wide, covering a massive floor area without the need for heavy internal load-bearing columns. When weight is no longer the primary constraint, a building can become a dynamic system that reacts to environmental forces instead of just resisting them. This Discover section illustrates David Fisher's 2008 design for a rotating skyscraper. By harvesting energy directly from the wind, each individual floor can rotate a full circle independently. The structure physically changes its exterior shape every single day while generating its own power. These material innovations changed the objective of design. Buildings were no longer monuments. They became flexible, active machines. That flexibility becomes a survival requirement in the deep ocean. Underwater, the crushing weight of the water column forces civilian architecture to adopt the engineering logic of a submarine. The Poseidon Undersea Resort in Fiji sits 12 meters beneath the surface. It maintains a habitable environment by relying on hyper-strong metal frameworks and specialized pressure-resistant clear plastics. Even dry land can be just as hostile. In the Antarctic, the ice sheet beneath the station is in constant motion, shifting up to 400 meters every year. A standard foundation here would be torn apart by the moving surface. The Halley 6 research station solves this by separating the building from the ice. It is elevated on hydraulic legs and mounted on giant skis. When the ice moves too far, the entire station can be towed back to its correct location. In environments this extreme, a building survives by moving alongside the landscape, rather than standing against it. But there is a final environment that offers no ground at all. The vacuum of space requires a structure to travel at nearly 8 kilometers per second just to maintain its orbit. The International Space Station serves as our current limit for human architectural achievement. It orbits roughly 350 kilometers above Earth, maintaining a pressurized, livable environment in a void. Standard construction materials are too heavy and fragile for this environment. The station relies on lightweight metals and massive outer solar arrays to capture the sun's energy, providing all the station's power. Because the station exists in zero gravity, it had to be launched into orbit in separate modules and assembled by hand. This photograph shows an astronaut performing a spacewalk to manually attach new parts, a modular construction process that never really ends. Space architecture required designers to move away from traditional construction entirely, proving that habitats can be assembled and inhabited in a weightless vacuum. We have evolved from fighting gravity with millions of tons of concrete to dancing with the elements using flexible polymers and hydraulic skis. The International Space Station represents a complete architectural departure from terrestrial norms, a research station that exists without the support of a foundation or the stability of a landscape. As we look toward future frontiers, the defining characteristic of our greatest structures will be their capacity for change. Future engineering demands we define buildings by their ability to shift, migrate, and orbit alongside the changing systems of the solar system.